right, welcome. So in this video, we are going to introduce what is meant by a geometric series and look at some important properties about how those series evaluate, because they do evaluate very nicely. So geometric series are series of the form a number plus a number times r plus a number times r squared plus a number times r cubed, etc. So a way of thinking about this is to say that if you take the terms of your series and just write them as like b1, b2, b3, and so on, if you took any term and divided it by the previous, you get a constant. In fact, the constant that you get in this case would be r. So if you took a r to the n divided by a r to the n minus 1, the a's cancel, the r's, well, all the r's except one of the r's upstairs cancels, and so going through the cancellation, you would get r every time. Another way to think about this is to get from one term to the next, you just multiply by r. So that constant that results, sometimes called the common ratio, because it's sort of like a ratio of subsequent terms, is common among all of them. It's just a number you would multiply by to get to the next term. So here's 4 examples of geometric series. So in one case, we have a common ratio of a half. Here, we're multiplying by a half to get to each subsequent term. Since each subsequent term is just a half times the previous, that means that we have a common ratio of a half. And here, the first term in our series, the a, that sort of seeds the whole series, is 1/2. In the second example, we also have a common ratio of a half. To get to each subsequent term, you multiply by a half. However, here, the first number in the series is 1 as opposed to 1/2. So these are 2 different series, 2 different geometric series. Despite the fact they have the same common ratio, they have a different starting term, which means they're different series as a result. You can sort of see it plainly here, but then it's even able to be seen from the establishment of the a and the r. Here's series 3 minus 4 plus 16 thirds minus 64 ninths and so on. Well, for this series, you actually can get from one term to the next by multiplying by -4 thirds. Multiplying by -4 thirds gets you the next term in the series, and the first term in this series is 3. Here's one that sort of doesn't even necessarily look like you can get from one term to the next by multiplying by a number, but in fact you can. 1 minus 1 plus 1 minus 1. You can get to each next number in the series multiplying by -1. So here the common ratio is -1, and the first number is 1. So at least we know what a geometric series is, and now we're going to look into how we can evaluate a geometric series. So to evaluate a geometric series, we are going to go about this how you would sort of evaluate any series at a fundamental level. You would look at an expression for its nth partial sum, and then you would want to take a limit of that expression. So it's possible that the limit of that expression would equal a real number, in which case you would get convergence. It's possible that the limit would equal positive or minus infinity, or maybe not exist, and you get divergence. Now, just so that we're all on the same page here, like if you just set r equal to 1, you would get a plus a plus a plus a. Assuming a was not 0, you definitely would diverge, like 2 plus 2 plus 2 plus 2. Definitely when you add up all of those, you get something that's infinite. So divergence is definitely possible here, but convergence is also equally possible. What if r was 0? In the silliest case, if r is 0, you just end up with a as the convergent value of your series. So certainly some geometric series converge and some diverge, and let's deduce which do what. So we're going to try to find the limit of the expression for our nth partial sum. And to do this, we're going to do something a little bit weird and bizarre, but just bear with me here. We're going to multiply it by minus r to both sides. So multiplying by minus r on the left, we get minus r Sn. Multiplying by minus r on the right, we'll get minus ar squared, minus ar cubed. We'll also get minus ar to the n and minus ar to the n plus 1. Just to be clear here, when you take the r and distribute it to the ar to the n, you'd end up with an ar to the n plus 1 term. But the way that I've written this out is sort of suggestive of what we're going to do next. We're actually going to add these 2 equations together, right? Because if each equation has equal things on left and right, you can add equal things to equal things and still get equal things back. So here we'll get Sn minus Rsn, just adding the 2 equations together here. But check it out. There's a bunch of cancellation that occurs on the right-hand side. The ARs cancel, the AR squareds cancel, the AR cubes cancel, all the way out to the AR to the n's, leaving just the A that's out in front and the AR to the n plus 1 that's out back. Now we want to try to figure out something about Sn. So to get Sn by itself, let's factor Sn on the left-hand side to get Sn times 1 minus r. equal to a minus ar to the n plus 1, and then we'll divide by 1 over r to get Sn equals a minus ar to the n plus 1 over 1 minus r. And so now we want to, here is actually a very nice thing. Here is a concise articulation of what you get when you add up the first n numbers of a geometric series. You get a minus ar to the n plus 1 over 1 minus r. And if we want to take a limit of this as n goes to infinity, note that limit is only affecting that r to the n plus 1 term, because a has nothing to do with n, 1 and r have nothing to do with n, so the n is only showing up as that r to the n plus 1. And please note here, if r is less than 1 in absolute value, then that's going to imply that the limit as n goes to infinity of r to the n plus 1 is going to be 0. The idea here is you're taking a number and multiplying it by itself many times. Even if you had a number that was close to 1 in absolute value, like 0.95 or something, 0.95 times 0.95 times 0.95 times 0.95 is getting smaller and smaller and smaller and smaller. 95% of 95% of 95% is retreating to 0 as n goes to infinity. If r was even closer to 0, like 0.1 or something, a tenth of a tenth of a tenth of a tenth is practically nothing. On the other hand, if r was bigger than or equal to 0, the limit as n goes to infinity of r to the n plus 1 diverges. And the idea here is take an r that's bigger than 1. Well then, what's going to be the issue here? A number that's bigger than 1, actually, let me just do it like this. Take a number that's larger than 1. This would diverge. In fact, this would diverge to plus or minus infinity, because what if you took like even a number that was close to 1 in absolute value, like 1.02? 1.02 times 1.02 times 1.02, this is like the classic sort of compound interest situation. That's going to swell to infinity over time because you're increasing by 2% and 2% and 2% in perpetuity. That would give you divergence to plus or minus infinity. This equation gives you some strangeness when r is equal to 1, I must say. So that's something that's worth noting. But I will say this, if r is equal to minus 1, then the limit as n goes to infinity of r to the n plus 1 diverges as well, because if r is equal to minus 1, then this is just minus 1 followed by 1 followed by minus 1 followed by 1, and that diverges. We've seen that oscillating behavior before. When r is 1, if you think about that, that was the case where we had a plus a plus a plus a, and in fact we would get divergence in that case as well. So that's maybe a special case. I'll write it down here at the bottom. R equals 1 implies our original series, going all the way back to the original series, is just a plus a plus a plus a, which would also diverge. Okay, but with that being said, you put all of these facts together, and what we get is, when you're looking at this expression for the nth partial sum of our geometric series, if we were to take a limit as n goes to infinity of our nth partial sum, well, there would be two cases that result. In one case, this r to the n plus 1 goes to 0, and then you would just get, well, if that r to the n plus 1 goes to 0, you just get a over 1 minus r when absolute value of r is less than 1. Because when absolute value of r is less than 1, that was exactly the case when the r to the n plus 1 term went to 0. On the other hand, when the r term was greater than 1 or absolute value, or in fact equal to 1 in absolute value, we got divergence. And so we get divergence when absolute value of r is greater than or equal to 1. But check it out. This is actually precisely the information that we wanted in terms of how to evaluate geometric series, because any series evaluates by taking a limit of the expression of its partial sums, and we just computed the limit of the expression of its partial sums here. So in the case where the absolute value of r is less than 1, what happens? Well, our series converges to a over 1 minus r. On the other hand, when the absolute value of r is greater than or equal to 1, our series diverges. And so, yeah, that's that. That's a wrap in terms of the developing a precise articulation of what a geometric series converges to. I'm going to pause, clean the slate, and then we'll hammer out a couple examples real quick. All right, so to hammer out some examples, here are 4 examples that we previously saw. So these are all 4 geometric series from a previous slide. And in the first case, we had r equals a half. We multiplied by a half to get to each term. The first term was a half. Well, how can we determine the convergence or divergence? Well, based upon our previous result, when r is less than 1 in absolute value, convergence. When r is greater than or equal to 1, divergence. Well, r is less than 1 in absolute value here, which means we get the convergence scenario, and we should converge to then a over 1 minus r. So this series here will converge to a 1/2 over 1 minus r. 1 minus a half. Well, let's see. This would be 1/2 over 1/2, which is equal to 1. And actually, if you remember whenever we computed this in a previous video, we found by other means that that series converged to 1 elsewise. So hey, the fact that we get 1 here is validating of a result that we saw previously. Now, what about this next series? Well, this next series also has a common ratio of a half. By virtue of the common ratio being less than 1 in absolute value, we know we have convergence, but what do we converge to here? Well, in this case, and in any case, whenever you converge, you'll converge to a over 1 minus r, which in this case is 1 over 1 minus r. Well, 1 over 1 minus a half is 1 over a half, but 1 over a half is 2. And actually that makes a hell of a lot of sense whenever you look at these first 2 examples, because the difference between the first 2 series is that the second series has an additional term of 1, which should increase the value of the sum by 1, which is exactly what our series formula did. So this formula is looking really good in terms of what it can do. What about the next example? In the next example, r was equal to minus 4/3, but that is greater than 1 in absolute value. And so as a result here, we necessarily get divergence because our r was bigger than or equal to 1 in absolute value. It doesn't matter what our a is, as long as our common ratio is bigger than or equal to 1, these terms are growing, and that's preventing the sum from being convergent. So checking out this last one, the r here was minus 1. Well, hey, when the r is minus 1 in absolute value, that's greater than or equal to 1, and so we get divergence in this case as well, because again, the r is greater than or equal to 1 in absolute value, and this also harmonizes with the result we've seen previously. We looked at this series through the lens of partial sums otherwise, and we're able to see the divergence from the oscillation that existed. Here's a final example just to show sort of how these things can manifest. This is in sigma notation. Sum n equals 2 to infinity of 3 to the n minus 1 over 5 to the n. If you look at the individual terms here, you'll get like 3 to the 1 over 5 squared plus 3 squared over 5 cubed plus, let's see, for n equals 4, you get 3 cubed over 5 to the 4th, and so on. Now this is a geometric series because here r is just 3/5. You just multiply by 3/5 to get each subsequent term. And here a is, well, 3 over 25, right? Because the first term was 3 over 25. Well, with this information, we should be able to utilize our result to figure out what this series converges to or whether this series diverges. Well, first, to determine whether the series converges or diverges, we look at the common ratio. Is the common ratio less than 1 or greater than or equal to 1 in absolute value? Well, in this case, the common ratio is less than 1, so we know that we have convergence. And in fact, as we always do, we'll converge to a over 1 minus r, which in this case is what? 3/25 over 1 minus 3/5. But 1 minus 3/5 is just 2/5. So we have 3/25 over 2/5. Let's see, a keep change flip there. We get 5 over 2. And put that all together, the 5 and the 25 would cancel. And then we just have 3/10. So hey, not bad. We just added up all of the terms of this series using the formulation that we concocted. So as you'll see, this formulation is about as sort of precise as you could possibly hope for from series. Difficult objects to grasp in general, but geometric series are so well behaved in terms of their structure that we can actually say a lot about their convergence and divergence.